Hey everybody, so in this video I'm going to discuss what's known as the chi-square distribution, and this is something that you would encounter in a probability or statistics course, and this is going to be hopefully kind of a one of two video part series, and I'm hoping this is going to be a one-stop shop. So whether you need a quick intro into chi-square, maybe you need a refresher, maybe you're taking the AP exam, I think this will get you a lot of the ways there in terms of understanding. So what is the promise here? In this video, I'm just going to, again, just really talk about what a chi-square distribution is and just try to understand it conceptually. So the next video, I will actually perform a hypothesis test involving a quote-unquote real-life example, and you'll see that that one will actually go much quicker. So hopefully it won't take too long. So, okay, what is a chi-square distribution? What does it do? So the idea is you're going to classify some data into different categories, and we'll do some examples here in just a second. Now, one thing I want to point out, these categories can be numerical or non-numerical. And the basic idea in a nutshell, it's right here. Do your expectations agree with the data you collect? And we'll see what we mean by that here in just a second. So let's look at a couple examples of where we might use a chi-square distribution. So suppose we go and collect some data, maybe we interview some students, and we classify them whether they're a freshman, a sophomore, a junior, or a senior, right? We're putting them into little buckets. Likewise, maybe we interview students in a particular class and we look at their final grade. Do they get an A, B, C, D, or F? Again, we put them in these little buckets. And maybe, we're doing some collection. Maybe we're interested in where people live. And we go out and we interview people, and if they live in the city, we're going to classify them by the last two digits of their zip code. So, for example, in the city I live in, people often ask, what's your zip code? I just give them the last two digits because there's a lot of common zip codes, or there's a lot of zip codes in my city, and those last two digits are enough to specify, roundabouts where I live. Okay, so you're going to go out and collect this data. So let's focus in maybe on our first example there. Maybe we go out and collect some information about some students, and we say, oh, are they freshmen, sophomores, juniors, or seniors? So notice in this case, we sort of have four different buckets, right? Freshman, sophomore, junior, senior. So in this case, our K value is going to be the number of buckets that we have, the number of different categories. So in this case, we would have four different categories. And more in terms of the technical terminology, we'll call those cells. So we have four different cells in this case. Okay. And maybe I'm going to go out there and I want to know the distribution of freshmen, sophomore, juniors, and seniors at a particular school. And, if I have no clue, maybe I just assume that there's going to be roughly 25% of each group. So if I go to the school, I could roughly expect 25% of the population to be freshmen, sophomore, juniors, seniors, etc. Okay, so suppose I go out there and I interview 1,000 students from a large university. What would I expect to see? Okay, so this word expect is important. What would I expect to see? Well, if I assume that there's 25% of each group, right? 25% of 1,000, well, I would expect to see of those 250 people, I would expect, of those 1,000 people, I would expect 250 of them to be freshmen, 250 to be sophomore, 250 to be juniors, and 250 to be seniors, right? That's what I would expect to see if I talk to 1,000 students and 25%, and I've got this nice even distribution. 25% of the population is going to come from freshmen, sophomores, juniors, seniors, respectively. I would expect to count 250 people. So this is going to be what's known as the expected frequency. So in my first cell, I would expect to count 250 freshmen. and then 250 sophomores, and then 250 juniors, and then 250 seniors. Okay, so one thing I want to point out is that these numbers are the same. These are the same in this example, okay? So they don't have to be the same, is what I'm saying. They are the same in this example. They don't have to be. And in my next example, where I actually go through a hypothesis test, I'll make it so that the proportions aren't the same. But in this one, hey, they are the same. And that seems like a reasonable guess. So suppose we actually go out there and we collect some data. So somebody says, hey, Patrick, at this particular large university, it should be, kind of the student body should be sort of evenly distributed. And then I go out there and I collect some information. So maybe now I actually go out there and put some boots on the ground and I collect my data. And I interview 1,000 students, and these are the results I get. Suppose 245 of them are freshmen, 261 of them, are sophomores, 252 of them are juniors, and 242 of them are seniors. And you can check if we add up those numbers, we do get 1,000 students. So now we can look at this observed frequency. So we kind of had our guesses, we collected some information. What did we observe? Well, in the first cell, which represented freshmen, we had 245. And in the second cell, we counted 261 sophomores. In our third cell, we had 252 juniors. And then we computed 242 seniors. So what do we do now? So to compute this statistic, this value of chi-squared, what we do is we sum up over all the cells. We just look at the difference between our observed values and our expected values. So we're going to compute that difference. We're going to square it, and then we're going to divide it by the expected number in each cell. So let's do that for this one. So this is going to be sort of this is going to be the formula that you're going to need to remember and compute when you deal with chi-squared. So in this case, notice, so if we fill in that formula, notice I'm taking my observed counts, so there's 245, 261, 252, 242. That's what I went out there and collected. And then in each case, I'm subtracting what I expected to see. Well, notice in each case, I expected to see 250 freshmen, sophomores, juniors, seniors, respectively. And then again, likewise, I divide it by that expected count, which again, in this case, is going to be 250 in each case. So I'm just using this formula. And at the end of the day, we get a number. And at the end of the day, that number that I get is 0.856. Okay, so that's wonderful. I got some number out. And now the important question here, well, what does that number tell us? Well, that number is going to tell us whether what we observed agrees with what we expected. And, well, how do we do that? We'll talk about that in another video, but that's the idea. So this number is going to somehow quantify whether or not our assumptions were good or not. And in this case, notice, right, if I expected 250 of each, so a little observation here, that's what I'm doing here in this next part. If I expected 250 of each, to me this would seem like a pretty, this would agree with my expectations, right? I wouldn't expect to actually go and get 250 of each. There's going to be some variability in the data. I would expect that to happen. But, 245, well, that's pretty darn close to 250. 261, that's pretty close to 250. So is 252, and so is 242. So intuitively to me, based on these counts, I would think maybe my initial assumptions were in fact correct. Maybe it is correct that 25% of the student body is each freshmen, sophomores, juniors, seniors. I would have no reason to doubt my initial assumptions, is what I'm saying, if I collected this data. And notice my test statistic here, this value of chi-squared, it's a quote-unquote small number. Okay, it's a small number close to 0 that's positive. Now, what if I went out there and observed some different values? So again, suppose I interviewed 1,000 students, and I found that 175 were freshmen, 300 were sophomores, 285 were juniors, and 240 of them were seniors. Well, okay, that doesn't quite agree with my initial assumptions as well. I could still compute this test statistic, just like I did before. And again, notice what I'm doing. It's the exact same thing. I'm taking my respective counts, 175, 300, 285, and 240. And I'm just subtracting away what I expected to see in each case. And again, I'm dividing it by what I expected to see. I'm adding those values up. I get some number. At the end of the day, in this case, notice I get a bigger number, 37.8. Well, it agreed less, I got a bigger number. So again, the question at hand here is, if we assume that our assumptions are correct, could we reasonably expect to see these counts, right? If it is correct that that the population is 25%, 25%, 25%, 25%, is it reasonable that I could have gone out there and collected this set of data? I don't know. Maybe, maybe not. That's what we're trying to answer. Let's look at one last extreme case. Suppose again I go out there and I talk to 1,000 students. Of those 1,000 students, none of them are freshmen, only 20 are sophomores, only 30 are juniors, and the rest, the other 950 students are all seniors, right? So, whoa, something weird's really happening. So intuitively to me, I would think, well, my original assumptions can't be correct. Well, okay, who cares? I'm still computing this test statistic the same way. I had 0 freshmen, 20 sophomores, 30 juniors, 950 seniors. Again, I subtract away what I expect to see and divide it by what I expect to see. And again, I compute that value. You can check my arithmetic. Notice now I got, again, a quote-unquote large number, certainly larger than the other two, of 2,615.2. And to me, I got this really large number. I certainly don't think, if I collected this last set of data, I would say, okay, my initial assumptions there's a very good chance, right, my initial assumptions are not correct, because I shouldn't be seeing this, is what I'm thinking. That's all chi-squared does, okay? So the question is, when is this number so big that it tells us something's wrong? That's all we're doing. Okay. So again, intuitively, a large value for this test statistic means that what we observe does not agree with what we expect to see. That's it. That's all that's happening in a nutshell. If you remember one thing from this video, that's the thing you should remember. Okay, so again, back to our question. When we compute this chi-squared, when is the number too big? That's to me intuitively what I'm kind of asking myself. Well, the answer is we're going to use tables and we're going to just use some hypothesis tests to address this question. And that's what I'll do in the next video. And it turns out there's just a nice decision rule that says, hey, depending on your requirements, that value that you compute of chi-squared, it's too big, or no, it's good enough to where you can still think your initial assumptions are reasonable. Let's look at a few properties of this chi-squared distribution. One, it's going to be a continuous distribution. Notice the value for chi-squared, that's always going to be greater than or equal to 0. And that makes sense because if you think of the formula, right, we had these observed values minus the expected value, and that could be positive or negative, but the point is we're squaring it. So we're always going to get either 0 or positive in the numerator. The expected value is going to be positive. Notice if we expected the value to be 0, if we had some expected value, like for example, I expected there to be no freshmen, for example, just don't even include that category. Just look at sophomores, juniors, seniors. So the idea is our expected count will always be greater than 0. Well, and that if we make those observations, again, this test statistic is always going to be greater than or equal to 0. The only time chi-squared would equal 0 is if your observed values agree exactly, right? They would have to agree exactly with what you expect. Right? So if I surveyed those 1,000 students and I got 250 freshmen, sophomores, juniors, seniors, I actually observed that. Well, chi-squared would equal 0 in that case. Okay, notice that so that's one of the property, or two of the properties. It's continuous, it's great, the value is going to be greater than or equal to 0. Notice it's going to be, well, not notice, we'll look at some graphs. It's going to be right skewed, and the shape of that chi-squared, it's going to depend on the degrees of freedom. And the degrees of freedom is going to be equal to the mean. And we'll talk about that a little bit more here in a moment. In general, basically, well, let's talk about it now, I guess. In general, what we're going to do to get the degrees of freedom, and there's going to be some conditions we have to satisfy, but in general, to get the degrees of freedom, we take the number of cells and we subtract 1 away from it. So notice in my example, I would have 3 degrees of freedom. So I don't want you to think that these two diagrams go with my previous example. I just picked some diagrams at random, just to point out some graphs of chi-squared. And I just want to point out a couple little things. So notice in my top graph, I've got a graph of, let's see, I can't get on there. So I've got a graph of chi-squared where the degrees of freedom is equal to 4. And notice at the bottom graph, I've got a graph of chi-squared where the degree of freedom is equal to 7. Notice that the bottom graph is shifted a little bit more to the right. And that's going to happen as your degrees of freedom increases, it's going to start shifting more and more to the right. Notice that the tails of these are a little fat, right? If you look at the tail, it's going to be fatter on the right side. It's going to be fatter on the right side, and that's all it means is to be right skewed. It's going to have a fat right tail. And those are just going to be some properties of the graphs. Okay, so the last thing I want to talk about is reading a chi-squared table. And this is going to be important in the next video, when we actually do a hypothesis test. So this is just a little bit of notation. So you're going to have this chi-squared of alpha, and this alpha is going to be important. That's going to represent a number such that the area to the right under the distribution is equal to alpha. Okay, so for example, suppose we want to compute chi-squared of 0.05 with the degrees of freedom equal to 10. So all I have to do is look for my degree of freedom, which is on the left side. Notice I look at the degree of freedom and I find that where it's equal to 10, which is right about there, you can see where it says degrees of freedom equal to 10. And then I just look where alpha is equal to 0.05, and I follow that over, and notice I get this value. So I've got the degrees of freedom is equal to 10, my alpha is equal to 0.05, and it says in this case that my chi-squared of 0.05, that's going to be equal to 18.307. Now notice in this notation, there's no mention about the degrees of freedom. So again, off to the side or somewhere, just recognize that we're doing this with degrees of freedom equal to 10. And again, pictorially, this is what's going on. So I've got my graph of chi-squared with the degrees of freedom equal to 10. If I look at the tail, I'm finding this value. And if I look at the area to the right of that, that area is going to equal 0.05. Well, it says the number where that happens is going to be 18.307. That's what that table is telling us. Okay, so one more time, 18.307. Notice I could look at chi-squared of 0.01. Well, intuitively, I would have to go out even further so that the remaining area is only 0.01. Well, again, I could read that from my table. So now I still have the same degrees of freedom. Notice I would still have the same degrees of freedom, but now my alpha is equal to 0.01. So now I would need to use this value, 23.09, and that would be the value here. 23, is that right? 23.209. 23.209 is what I mean. Okay, so that's how we just read off the value of chi-squared from a table. Well, let's put this all together, and in the next video, we will actually perform a hypothesis test, and you'll see that it's actually going to be pretty fast. All we're going to have to do is compute our chi-squared. We'll be given some value for alpha. We'll compute that test statistic, and there's just going to be a rule that says, nah, it's too big or it's not. So, all right, I hope this quick little introduction helps you understand what chi-squared is trying to do. And again, in the next video, we will actually go through a quote-unquote real-life example so you can see how to perform a hypothesis test using the chi-squared distribution.